Thank you, Tom. It's an awful title, an impossible title. It was the best thing I could come up with on the spot. My talk's only going to take the smallest step in the pathway between mind and brain. I'm going to stay away from philosophy, won't worry about defining mind. Really going to try to talk about the relationship between neurons, the nerve cells on which all the activities of the mind are based, and memory, associative memory. I could just try to describe the relationship that I will develop by analogies. Look, we've all been driving on the New York Thruway or the Garden State Parkway or what have you, a road with relatively limited access to new vehicles coming in from the sides. And traffic's light and you're going 70 miles an hour, traffic gets a little bit denser, you drop down to 65, maybe 60. Later in the day, the traffic's denser, and suddenly you're going along at 20 miles an hour in this very, very dense traffic, and you think there's an accident up ahead. For no reason whatsoever, traffic opens up and you drive 60 miles an hour for 3 minutes, and then you get in one of these things. You get in this bunching phenomena, the stop-go traffic phenomenon. Now, this doesn't have anything to do with the traffic coming in from the side roads, really. It's something which happens just because the traffic is dense. Now, how does it happen? Look, your typical car driver, Joe Sixpack, is only looking at the car in front of him. He never even looks in the rear mirror. And he simply adjusts his speed according to what's happening to the car in front of him. And somehow, when you have a simple unit of that sort, adjusting the car's speed, the interaction between a large number of cars generates all kinds of interesting traffic flow consequences which you wouldn't have anticipated from the way those individual units work. And in this case, I spoke about an elementary unit, a car, which had one of its very interesting things which was changeable, but a property of any particular car at a moment, its speed. And the car interacts with other cars, not through colliding with them, hopefully, but through a driver looking at what's going on in the car ahead and maybe the car behind and aside, but just looking very locally. And the result of having a large number of cars, each adjusting its speed, each interacting with only a few others around it, you have a large-scale phenomenon of traffic bunching or stop-and-go traffic. In another system of that sort, you have individual molecules. The atmosphere is made up of a huge number of individual molecules. They have velocities, that is to say, they have speeds, but you have to say which direction they're going as well, so I call it velocity. And they interact by occasionally colliding. Sometimes they just bounce off each other, sometimes they stick together. And that, just a large number of those simply doing those simple things gives rise to weather, clouds, hurricanes, all these large-scale phenomena which we could be interested in for the atmosphere. Look, you can say the same thing about a stock market crash. There are all the individual traders doing simple things, and yet the interaction between all these people produces all the rich phenomena of nervous stock markets and stock market crashes and so on. And in the case of neurobiology, there are nerve cells, and each cell has something which I'll call its activity, which is sort of like the speed of the car in the analogy which I've given. And these cells interact through connections. They're synapses. And as a result, out of a large such system, a system of about 100 billion such cells, you have all the phenomena of psychology, memories, perception, and so on. Now, in describing one of these things, you can't describe everything at once. If I want to describe traffic, I'm going to make a description of the car as I've given it to you. I've omitted to mention the fact that cars have wheels, engines, and so on. Similarly, I will omit mention of all kinds of details of what goes to make up neurons. It's very difficult to describe those, as Pat Churchland would have remarked earlier, and at the same time talk about the level as high as psychology or memory. All right. So what aspects of memory would we like to explain? The kind of memory that I'm going to work to describe is often called associative memory and declarative memory, the kind of memory that we have for occasions. You know, you could come to reunion and you'll go back home and you'll remember having dinner last night in the graduate college, and a few of the words that President Shapiro may have said before dinner, and that you sat next to Joe Hurley and argued politics with him and so on. And if a few days later you're reminded of one part of this, you'll be able to get hold of the other part of it. That's just the way your memories work. But things are associated, and then a whole bunch of facts are linked, and if you get hold of some of them, you get hold of others which are linked to them. And that associative memory is entirely different from the way memories are stored in computers. In computers, you look at the hardware, and the way the hardware works is you store something somewhere at an address. If you store Tom Langfit at address 559, then in order to get the name, you have to say, address 559, what's in it? And we'll say Tom Langfit. If you remember Tom, no help. The computer says, yeah, where do I look? And so memory is by address. And it's very different then from associative memory. We have no notion of address. In computers, memories are highly localized. I mean, look, here's the way computer memory fundamentally is something like this. You write something on a page. And, if that nerve cell happens to die, it's gone. On the other hand, if you write things on the book slightly differently, if you share the memory somehow, if you don't have it on a specific page, you see PU stays quite nicely on the edge in spite of ripping out the page or even 10% of the pages. And that's part of the reason why, while you're listening to me today, this afternoon, about 3,000 nerve cells will die in your brains. Nevertheless, you don't forget something specific. You don't forget your wife's middle name as a result of that. But what happens more is there's a gentle degradation of everything you do. And that's another of the properties of associative memory that one would like to understand. Well, how is information represented in the brain? And what is the associative memory process? I'm now going to turn to talking about those two issues. And in so doing, I will oversimplify the system considerably, and yet that oversimplification, I believe, still contains the absolute essence of what's going on. I remember in my early days of teaching, somebody described pedagogy to me as the art of telling lies in order to convey the truth. I'm not going to lie to you, but there are a whole lot of qualifications of everything which I say, which I might like to include, but then again, this is not a 3-day lecture. Suppose you look at some typical visual scene. That was a picture of my research group at Caltech. What are the cells in neurobiology doing? First of all, cells, an individual cell talks to other cells by putting out pulses, which are called action potentials. And if a cell is very inactive, it's just sitting there quietly. Or if a cell is slightly active, go making a click every second or two. Very, very active cells put out about 500 pulses a second. And a cell can do anything in between. Neurobiologists have, over the years, studies in higher animals, been able to understand things about what individual cells respond to. For example, in a relatively early part of the visual cortex, you may have a cell which responds when you are looking here to the fact that this is a blue blob located here, and if you had the picture everywhere the same and you were looking in the same position, but change that blue to green, a different cell would respond. And Charlie Gross in psychology here some years ago discovered cells which don't seem to, in monkeys, which don't seem to respond to anything else but faces. And so the activity of those cells occurs only when faces are in the visual scene, and nothing else in the visual scene seems to drive those cells. And in some sense, the activity of those cells represents the presence of a face. Suppose you don't have a visual scene, but are remembering one. What does it mean to conjure up a memory? What it has to mean fundamentally is that you've got to be able to get the kind of activity pattern in the cells that matter, presumably in the parietal and frontal cortex, the same kind of activity pattern that you would have had the stimulus really been there. Then, for many purposes, other cells in the brain will be able to read out these activities and say, that's just as if Joe was really present. And in that sense, you have a memory. So the way a memory, and it really has to work, a long-term memory, is to be able to invoke a pattern of activity which is related, or so it's essentially like the pattern of activity which was invoked long ago by a real stimulus. I'm going to try to build the idea of associative memory up by nuts and bolts and what the associative process is. Here are 4 people that I know, their heights and their weights. I suppose this is all I know about the people. Then I just have just a few facts, and associative memory is supposed to be able to do something like the following. If I say 69 inches high, it's supposed to say 245 pounds. If I say 170 pounds, it's supposed to say 72 inches. Or a good associative memory even corrects hints which aren't quite right. So if I said 110 pounds, the associative memory should, in some sense, say, you're close, but you probably mean 105 pounds and 65 inches. Because somebody doesn't have to remind you exactly of something in order for you to pull out the memory. If there are enough things there that are roughly right, you can pull out the memory and even correct the clues that you've been given. Now I can represent that same idea this way. I now think of this coordinate axis as representing the activity of a neuron whose meaning, as it were, is the weight of something, and this one the height. And if the activity pattern is this, then it means it's got 240 units of activity of this one, and it's got 69 units of activity of this one, and it means that's sort of the pattern which, when this particular person was there, should be produced. And it means also, on the other side, that this is the pattern of activity which you'd like the system to have, so it can essentially read off the coordinate axes when it's recalling something. And you'd like it to know these 4 things, and so, well, it's just a graphical way of representing the same information that I had in a tabular fashion on the previous view graph, except now you can see that I could relate this tabular information to just the activity of a couple of nerve cells. So here are the 4 things that you know, the 4 people that you know. Supposing you're given information which says, 240 pounds. You'd like then, you say, go up here. I should have a pen, never mind. And if you're given information, 130 pounds, it says, go here. Supposing you're given rough information, well, it's 230 pounds and 64 inches. That's starting here, and you'd like to say, well, that's not right. Let's move over to here. And the idea of an associative memory is essentially the idea of starting with approximate information, approximate knowledge in one of these locations. And the associative memory process just says you start with that approximate activity of the cells, which comes from somebody saying, do you remember Joe? And then you move from that activity to the activity pattern which actually represents the entire memory. So the idea of associative memory is fundamentally that you have some patterns of activity to which you move, and you'll move to one of these patterns of activity and stop moving no matter where you start. So if I start here, I'll move to that one. Start here, I'll move to that one. And these patterns of the particular patterns of activity where you stop and you stay in that pattern of activity are really what your memories are. And the recall process is the process in which you start somewhere from a clue you're given, and the activity changes in time to get to that location. Now, because I can easily draw in 2 dimensions, of course I draw that pattern in 2 dimensions. But if you want to have friends who have names, you have heights, weights, and you draw another coordinate axis which has the names out along it, and then a particular person can have an additional characteristic, a name. Since you have many, many nerve cells, there's no difficulty in conceiving of spaces of thousands of dimensions in which this basic idea still works. The values on the coordinate axes are the activities of cells, and you start somewhere and you settle down in a particular point, and the values of the coordinate axes represent the information in the memory, like the heights and weights of the people involved that I've been telling you about. So that's the associative memory process. Now, how does it actually take place in neurobiology? There are 2 things which are important. One is that we have this process which, after we have a memory, our activity can start somewhere by a clue we're given and move to that target, to that memory, and have an activity which is appropriate. The other thing is we must have a process which allows us to put memories where we want them. I'm going to talk first about the question of how it is that this whole system can work, how it can have activity which changes in time and settles down to a particular pattern. You've been shown nerve cells before today. Here's a sketch of a typical nerve cell. It's got 3 important parts from my present perspective. One is a cell body. The other is an axon which goes out and branches and makes contact with the other cells. And the third are the dendrites, which receive contacts from other cells. What I'm describing here is really an input-output system. The cell body is what generates the action potentials. They're broadcast out to other cells here, and I get inputs from different cells here on the basis of which this cell decides how much activity to broadcast out. And so every 6th cell is simply broadcasting activity based upon the information which it's receiving in on its dendrites. The stable patterns of the system are then going to depend on the cell-cell interactions, on the connections between the cells. And let me just try to illustrate how that goes in the simplest way that I can. Supposing I have 2 neurons, and I'll think of the activity. So here's one neuron, here's another neuron. I'll think of the activity in a neuron. If it's strongly active, I raise my hand. If it's inactive, I put it down. Supposing I have 2 neurons which in their anatomy are connected by excitatory connections. That means from A's point of view, if B is active, A should be active too. And from B's point of view, if A is active, B wants to be active. That is to say, the action in B turns on action in A, and vice versa. How does this system behave in time? Well, supposing I start with both neurons very active. A will look at B and say, oh, B is active. That means I'm supposed to be active. I am active. I'm fine. B will look at A and say the same thing, and so they'll just stay there both active. If, on the other hand, I started with both of them inactive, A will look at B and say, B isn't doing anything. Well, therefore, I should be inactive. B will look at A and say, no reason for me to do anything either, boss. And so the system will just stay there like that. If I started with a system like this, with A active and B inactive, A may look at B and say, no reason for me to be active. Then B looks over, no reason for me to do anything either. Or it could have gone the other way. B could have looked first and said, oh, I should be active. And then A looks over and says, I should be active. But in either case, if I start like this or like this, I will after a while end up like that or like this, just by following these very elementary rules. And so there are only 2 patterns of activity which this system will result in after a while. No matter how you start it, either both will be active or neither will be active. Now, in neurobiology, there are really two different kinds of connections. There are connections, so if a cell is active, it tries to make another cell active. Those are excitatory connections. There are also inhibitory connections. So if this cell is active, it may tend to suppress the activity of another cell. Here's two cells connected by a slightly different activity pattern. The anatomy says A excites B, but the anatomy says that B inhibits A. That produces rules which are just a little bit different. And now you can see the consequences. Supposing I start like this, A and B are both active. A looks over and says, B is active, therefore I should be inactive. So A turns off. B looks over and says, A is inactive, so I should become inactive. And then A looks over and says, oh, B is inactive, so therefore I should be active. And the system will just keep going like this and never stop. And the different pattern of how the activity pattern changes with time, you can see is just entirely different and it depends upon the way the connections are between the cells. Now, for some purposes, you need activity patterns which keep changing in time. Goodness knows, if I'm giving this talk, if my activity patterns sort of went to a stable state and stopped, it would just end there. Or if I'm walking across the floor, I have to generate an activity pattern which is cyclic. But for things like retrieving associative memories, what you need is the neurons which are involved in those memories to go to one of these stable states and stops. And you simply have to have connections of such a sort that they'll do that. And in the case of associative memory, the reason the connections are like that turns out to be very simple. If you associate orange with tiger, you also associate tiger with orange. And so association tends to be a two-way street. So going back, this is the kind of movement pattern, the way the activity changes with time, that you need for an associative memory. Of course, I need it not just in a movement pattern in 2 dimensions, but I need it in a large number of dimensions. But it's a very special kind of movement pattern. It says no matter where you start, you'll go to one of these designated points and stop. How can you understand that kind of movement pattern? Well, here's a system which has it. It's called the tufted mattress. Supposing I have a nice tufted mattress and I drop a ping pong ball on it somewhere. You know what will happen. The ping pong ball, if I drop it near this tuft, will roll down in that valley. If it rolls in this, it'll drop down that valley, and so on. And so the pattern of motions, no matter where I drop the ping pong ball, it'll go over to one of these valley bottoms and stop. And so if I just draw how it moves, it's exactly this kind of thing. And so things which move only in this kind of way, that go to particular points and then stop moving, are often easy to understand. And the thing which they have lying behind them is this idea of height. You understand that the ping pong ball rolls to one of the tufts just because things roll downhill and there's a little bit of friction, so you stop in the bottom of a valley. Similarly, in the equations which actually describe the way the neural activity evolves with time, there is a mathematics which generates something which is equivalent to height. And you can understand how the equations work by saying all that's really happening is that you're rolling downhill, and the memories simply are valley bottoms. And that analogy is very, very close in the mathematics, and it allows us to talk about some of the phenomena of associative memory in ways which are interestingly predictive without actually ever writing down a line of mathematics. For example, Why is it that if I want to remember somebody's name, remembering some nonsense rhyme connected with the name actually makes it easier to remember the name and recall the name again? Well, if I take one of these, if I take a mattress, I'll roll in here equally. All these are sort of equal. But if I want to remember one of these better, that is to say, if I want to be able to access it more easily, I'll push it down further. If I push it down further, there's a bigger catchment basin from which it will find a ping pong ball will go to that one compared to other ones. And the simple idea that if I have a system and I build deeper valleys, then the catchment basin goes up, and I'm more likely to fall into that catchment basin and thus roll down to the bottom of the valley. That simple idea is one which makes you understand why it is that just remembering something which is bigger is easier to access, because it turns out that the depth of these basins is related to the number of items which are in the individual memories. Or here's another thing which you know can happen. Under some circumstances, everything there's some traumatic event which has taken place, and as a result, things which otherwise would remind you of other things now remind you of that traumatic event. Supposing in this mattress case, I simply push down very hard on one of these. I make a very deep valley there. That's a very strong memory. I'll have a big catchment basin. And you can understand that there's those dimples in the mattress which used to catch ping pong balls set near them. If I make a deep valley, the whole thing tends to tilt. And those dimples are now on the side, and they're not deep enough for anything ever to stick in them. And as a result, if you start up here, instead of falling there, you fall down here and remember the very, very, very strong or traumatic memory. If, on the other hand, you could remove that strong and traumatic memory, come back up, a dimple which is on the side can once again become a basin, and you'll understand why that memory can become accessible. And this helps you understand why at some times particular memories are accessible, and why under other circumstances that same memory simply seems not to be accessible. Or yeah, here's another of the same. Let me go back to that again. If I take a flat mattress and have these dimples in it, then no matter where I start, I'll run down and find one of these memories. Now, there are quite different categories of behavior. Now, none of you understood that I said categories. And the reason that you didn't is the following. That you know, there are a bunch of words that you know, and if I make a sound which is somewhat like a word, near a word, you will say that must be the word that I said, or like this word must be this word, and so on. But if I make a sound which is too far different from any word that you know, you'll simply turn off and you say, I don't recognize a word. All you need to do to understand how that occurs is to understand that if I make this mattress flat, no matter where I start, I'll run down to one of these divots. But if I tilt the mattress a bit, then if I'm close to one of these little dents, I'll roll into it. But if I'm off in the middle space, I'll roll off the mattress. And so the question of going between something where you are forced to make a category regardless, or where you reject something and say it's a non-word, is one which is a minor adjustment in the overall landscape terrain that you're functioning in. And so when you listen to a non-native speaker mangling English, you basically put your mattress flat, and no matter what is said, you try to make it into a word. These are a few of the many illustrations that can be made which make connections between the ideas I've been describing of associative memory and based on neurons, based on mathematics, based on fairly simple descriptions of what neurons are doing, and some of the things which are known at the psychological level. There's one particularly interesting one which I will mention, which is only a surmise, but a very interesting one coming from Francis Crick. Real nerve cells have elaborate structure. Each of these big blobs is a neuron. You can see elaborate dendritic structure from each neuron. And if this were in more detail, each of these would branch out into more fine branches. And the connections which are responsible for the memories have to be made when the memories are put in. They're made, one believes, by a mechanism which is similar to what's called LTP, something which is studied also here in Princeton by Zhou Qian in molecular biology. However, when particular memories are made, some connections have to be strengthened somewhere. And where are these connections? Francis Crick was suggesting that as the brain develops, that these dendrites spread out, become more richly branched, and as you learn things later in life, the connections responsible for them are further out in this dendritic tree, in the arbor of this dendritic tree. He then suggested that at the same time as the brain begins to decline, one of the things which happens is the dendritic arborization tends to retract and the finest arborization lost. And that's a very interesting description of why it may be that as one gets older, some early memories still remain very vivid, whereas later memories can actually be rather hard to access or may be lost. Must mention one other interesting aspect of this memory process. You have to be able to put new memories in. Putting new memories in seems to be a process of having the system in a certain state of activity, a state of activity which corresponds to the circumstance you're in now, and then making synaptic changes which will allow that state of activity to persist later. Now, what you're doing from this height, from this landscape terrain, is building a dent in the terrain for a new memory. So someplace where there was no dent, you're putting a dent, and that's now something you can roll down into and is a new memory. However, you have this very complicated geology on which you're trying to put a new dent. Question: if I put a new dent here, can I also create a valley bottom somewhere else which corresponds to nothing I've ever seen? Can you have false memories, in short? Psychologists know that you can have false memories, and one of the things which this same mathematics shows is that you can have false memories. If you keep putting dents in this terrain to make true memories, you also tend to get some dents which are shallower, but represent stable points which are possible of being recalled even though the event which corresponds to them never occurred. Now, this may be a defect if you're trying to remember people, if you remember somebody that doesn't exist. If, on the other hand, you're thinking about something like chess, you have all kinds of chess positions you've been in before. Here's a situation which is somewhat like several other things that you've been in. Maybe what you like to remember is not the move you made in these other things, but a move which you've never made before because the situation is a little different. In some sense, imagination or brilliance, inventiveness is something which actually may be associated with these minima, these local valleys, which are not things which you've explicitly made. Well, I've tried to bring you somewhere along the road between the neuron and a phenomenon of psychology, a phenomenon of mind. The picture I've given is very oversimplified. You certainly have to do some mathematics if you want to describe things well and check the consequences of what I say. But if, on the other hand, you just want to understand it, the picture which I've given you is a very good description of an enormous piece of mathematics. Thank you.
She has